Thanks a lot for the invitation and the very kind introduction. And it gets even worse in terms of connections. We also used to have an Air Lab in Delft, which stands for AI in Retail. I'm going to show one video later today. But now we're done with that project, so you're free to have that name. Oops. It's actually going to connect very nicely with what Francesco was talking about. I'm going to take a slightly different stab at robotics and learning. What I'm going to talk about today are really specialists, but with the idea of being able to learn so quickly and directly on the real robot that you don't need to go through the effort of collecting massive amounts of data, doing lots of learning in simulation, and having very big networks. But I think there's lots of also interesting ways on how you can connect them. Okay, so just a little fun illustration of what I'm interested in. It's also motor skills. Francesco had that on one of his slides. So that's movements on the order of a couple of seconds to maybe a minute. So something like flipping a pancake or a kick in robot soccer, that would be one motor skill. And then you would chain those to achieve more complex tasks. That's not my laptop, so it's not my fault. Maybe you need to plug in the power. Okay, let's see. Yes, no, maybe, good. Francesco already mentioned collecting demonstrations and then having the robot imitate that, so it'd be imitation learning, or robots having their own definition of success and then practicing on their own, which is reinforcement learning. And that's also very much connected to how humans learn. What I'm going to talk about today is also inspired by how humans teach and learn. That's interactions with teachers. So if you think about a little child, he or she is going to interact constantly with its caregivers, who are going to provide encouragement and feedback and instructions. And the same if you're learning a new sport or learning to play a musical instrument. So that's teaching through interactions, where the idea is that you are going to have some form of intermittent interaction with a teacher or a coach. For instance, additional demonstrations or providing some kind of feedback while you're actually still learning. And that's something you see more and more in robot learning. I believe there are big benefits to approaching robot learning in this way. It drastically speeds up the robot learning, which enables the robot to learn more complex tasks. And hopefully that's also a somewhat intuitive way for humans to interact with robots. And we're actually quite good at that. And it's not only other humans, but also other agents where we apply these kind of strategies. I'm going to first talk about applying this idea in the setting of reinforcement learning, so learning by trial and error. And then the second half of the talk is going to be about applying that in imitation learning. Before we do that, I'm going to show you a very old example on reinforcement learning, learning to play ball in a cup, so to catch the ball in the cup. My cousin's daughter was around 10 back then. Took her 35 times to achieve the task. For an average adult, that's maybe around 20 or so. Also here we started with providing an initial demonstration. If you just mimic that and play it back, it kind of works, but it still misses by a few centimeters, and then it starts trying out different strategies. It gets closer after some 40, 50 trials or so. It usually bounces off the rim, but sometimes goes in, and after 100 trials or so, it has converged. So roughly same order of magnitude as human learning, and we were quite proud of that back then. And in a few minutes, I'm going to show you how you can do even better if you include a human teacher in the learning loop. Okay, so how would that look like? I can go very quickly over that because it's exactly the same thing rotated 90 degrees that we saw a couple of minutes ago. So we have the environment, states, actions, and the robot has a policy that decides on which action to take in every state. You could have a reward or cost or goal definition there additionally, but what I'm going to focus on is having a teacher there additionally. he or she is going to be able to observe both the states that the robot and environment are in and the actions the robot takes. And now what the teacher is supposed to do is provide some kind of feedback to the agent. You could go to two different extremes there. You could say, let's just have the human teacher provide an evaluation. In the simplest case, that's just binary. Success, 1, failure, 0. It's probably very easy to do for a human teacher, but then you get the typical problem of having very sparse rewards in reinforcement learning, so it's very tricky for the robot to get meaningful information out of that and explore on its own to get the one success. On the other end of the extreme, you would say, let's just have the human teacher provide the perfect action the robot was supposed to take in a certain state, which can also be very demanding for a human teacher. So the examples I'm going to show you in the following are somewhere in the middle, and what I also have here on the slide, we're going to have corrections. A correction on the action, so it's saying you should move more to the left, more to the right, move faster, move slower. So it's more like a gradient and not telling the robot the absolute offset, but just a direction in which it's supposed to change. Many of the things are based on an idea from an algorithm that one of my postdocs developed. It's called COACH, Corrective Advice Communicated by Humans. In this very simple illustration, the idea is the robot drives down from the top to the bottom on the right side of the road. It has some initial policy, it's not great, but then you have the teacher who is jumping in once in a while, providing corrections, literally move to the left, move to the right in this case. It's going to integrate that into its current policy, and hopefully the next iteration is already going to do a lot better, and the human needs to jump in less frequently. And then in the end, hopefully the robot or little car in this case can do the task on its own. So coming back to the ball in a cup example, we could say, okay, let's replace the initial demonstration, for which Katharina, my colleague, actually also had to practice quite a bit to get it right, by using this kind of interactive approach of correcting the robot's actions and coaching it to do that successfully. And then let's fine-tune it with reinforcement learning again. But we can actually do better and do all in one combined approach. For reinforcement learning, one of the important components is exploration. So the robot trying out new strategies to see what works and what doesn't. Very classically, that would be some random exploration using a normal distribution or some Ornstein-Uhlenbeck or whatever. So now what we did here in this paper is we also modeled the interactions with the teacher as a form of exploration. And that allows us to very naturally integrate that into a fairly classical policy search approach. Policy search, so that's effectively actor-only reinforcement learning, where you're directly trying to optimize the policy. In an episodic setting looks something like this. I don't think the laser pointer is visible, so I'm just going to very quickly talk you through it. So you do multiple iterations, you try the same task multiple times, you do some exploration, so you modify it a little bit, and then in the evaluation step, the robot figures out if the thing it tried worked better or worse, and based on that you update the policy parameters. So that's how a typical policy search approach would look like. And now what changes if we do that interactively is that we have the option for the human teacher to jump in and to provide corrections. We have a hard switch there. If the human jumps in, then we're going to switch off the autonomous exploration, because it tends to get very confusing for a human teacher if the robot is trying random stuff while you're still trying to correct it. And what's also very important, what we figured out, is that as a human teacher, you can directly see the effects of your correction. So if you press a button to tell it to move more to the right, it should directly start moving more to the right. That really helps to figure out if your correction was successful, and to get the policy to improve. So it looks something like this. Now we can actually start from scratch. So initialize it hanging down without any initial demonstrations. What you can see is Carlos sitting in front of the robot using a keyboard, providing these corrections on moving in which direction a bit more, and the velocity. And then after some 20 trials, it can actually catch the ball in the cup. And here's a little slow-mo. So if you look then at some plots, we have on the x-axis the number of rollouts, so the number of times it tried to do the task. And on the other axis, that's the cost, so lower is better. In red, you see what happens if you try reinforcement learning from scratch, just using more or less the distance between the ball and the cup as a cost function. It takes some 200 trials or so. It was a lot faster if you kind of initialize it with a good initial policy, and it just needs to fine-tune. In green, you see what happens if you use only the interactive imitation learning. So it's just a human teacher providing corrections, but the robot not trying to optimize it on its own. And in blue, that's the combined approach I was talking about. So you can see that for both interactive approaches, it learns very quickly in the beginning, so some 20 trials or so. But then for the green one, if you look at the end, at some point, it just flattens out because the human teacher reaches his or her capacity of how fine-grained you can do the corrections. If you combine that with the robot doing reinforcement learning on its own, you can see that we get a better final performance. Initially, it takes a tiny little bit longer, but it's actually compensated by having a better performance in the end. So that really plays to the strength of both the robot and the human teacher. You mentioned the high jump. Kind of a human teacher would be very good at figuring out the Fosbury flops or the new strategy. And then the robot is very good at doing that very reproducibly and actually fine-tuning the movement. And then what you also very nicely mentioned, one of the big kind of assumptions we make here is that the objectives of the robot and the human are aligned. If the human teacher is trying to provide corrections that go against the optimization criterion of the robot, then yeah, you're going to be in trouble, and it's probably just going to slow it down quite a bit, and you won't profit from the inputs of the human teacher. So that much on using reinforcement learning with a teacher in the learning loop. And now I'm going to switch to imitation learning. So there the setting is that whatever the human teacher demonstrates, that's by definition the correct thing the robot should do. It does not have any own objectives. It's trying to optimize in parallel, maybe except for some lower level safety layer stuff. So also here we try to learn directly from images using a comparatively very simple neural network structure with a few convolutional layers going to a compact latent representation. That's the part in purplish there. And then we have image reconstruction, so kind of an encoder-decoder structure as one of the auxiliary criteria, and the main objective is to learn, again, the policy, so which actions to take. You could go the way of saying, okay, let's pre-train the kind of the perception to get a good latent representation, which would mean you need some data related to the task beforehand to train that, and then once that's kind of converged, you start training the policy. Turns out it's almost as efficient to do it directly in this combined way, and the final performance is actually better. So why is that? The thing is, initially the robot doesn't know anything. It doesn't know how to do the correct behavior. So effectively, in the beginning, the human teacher is going to remote control the robot anyhow. And by the time it has learned how to mimic the actions of the human teacher sufficiently well, also the perception part has converged sufficiently, so that very nicely plays together. So how does that look like? Here's a little example in Duckytown, one of my PhD students using a keyboard, which you can see once in a while to provide the corrections. On the top you can see the very bad camera image, and on the bottom you can see the even worse reconstruction thereof. In this case, we really did not care about the quality of the reconstruction. It just needs to be good enough to be able to do the control. So you can see whatever you get, the lane markings and boundaries, and everything else is very blurry. And then what you can do is actually some kind of instantaneous validation. Take your hand off the keyboard, you see how well the robot behaves. If you're happy, great, you're done. If not, you just continue providing a few more corrections. So within really a couple of minutes, you can teach a robot to drive deer. That was without any real interactions with the environment, but things become more interesting if you actually are touching things or you have high-speed movements. In the next approach I'm going to show you, we actually wanted to not only learn the trajectory and actions of the robot, but also the stiffness parameters so it can exert forces on the environment. There we started with a kinesthetic demonstration, taking the robot by the hand and moving it around. Because we didn't have a force torque sensor, they are kind of recording the precise forces and interactions wasn't possible, and that also doesn't work for correcting it that well. So once we have this initial demonstrations, we actually switch to a different interface. In this case, it's going to be a space mouse. And what the robot is learning is at the same time a trajectory. So that's the part in blue. So it's an attractor field using a Gaussian process in this case, and a stiffness profile. So that allows us actually to have a stabilizing field that pulls the robot back to the nominal trajectory. And I'm going to show that in a second. So here's a video of a very classical whiteboard wiping task. Anna is providing 2 demonstrations in this case. If you play it back, you can indeed tell that it didn't figure out that it needs to apply a force or have the attractor of the controller below the surface. Now she is going to push down on the space mouse to indicate it needs to move more lower, and at the same time what you saw on top here is it's adapting the stiffness parameters of the robot. So that was just one iteration of corrections, and then you can try that out. And it already works. Then that's the Air Lab example. You can see it there. It's about restocking in a supermarket setting. And there it's really all about speed. So we wanted to get it down to below 5 seconds. Now it's still sped up. You can see yet another interface we use for the corrections. So it's a kind of game controller. And what we're doing here is we are correcting both the trajectory and the velocity separately. One other interesting tidbit is that the timing of the robot gripper is very inaccurate. It's plus minus half a second for us. So also there, the teacher needed to come up with a strategy that is robust to the exact timing of when it closes the gripper. Okay, and now here in real time, putting the milk carton in the shelf. There we also did a few experiments and user studies in a slightly simplified setting. If you have some kind of perception there, it can also adapt to the movement of the objects. And because the behavior is based on uncertainty, if you move away too far from the data it has seen, it becomes so uncertain that it just stops until you bring the object back and it knows again what to do. So those so far were tasks a bit in isolation. We also participated in a competition last year and the year before, which is about solving these kind of task boxes. This one is vaguely inspired by disassembling and recycling electronic products, which has many, many different steps in there. So here, one of the steps was unplugging and plugging it in somewhere else. What you're going to see here now is it's also doing some kind of a recovery behavior, spiraling. Many of the tasks are very precise, so actually there really visual feedback is needed as well. And again, start with an initial demonstration, and then we use a couple of rounds of corrections to get it there. And then we combine it with these additional modules and some higher level sequencing of the tasks. Here is a video of the a complete run. I probably won't be able to show all of it, so that's now in real time actually. So one of the cool ideas our human teacher came up with is not having a specific gripper, but actually use the cable in this case to open the lid. Now it's going to do the plugging in. Okay, what else is there to say about it? So in the moment it's going to take out the probe there. Taking it out is obviously fairly easy. Getting it back in was surprisingly challenging. You can't really see it. It's like a hole in the middle and another circle around it. So if you get the tip in the circle, then it gets stuck. And they need to be a bit more smart about detecting when it goes wrong, or learning to detect when it goes wrong, and then fixing it. And the final part, which we actually thought would be very hard, but turned out to be very easy, is wrapping the cable around these two hooks you see a bit on the left. Okay, in the sake of time, I'm going to wrap up the talk. That video is also online, so if you're interested, you can see that on YouTube. So, to sum up, I was talking about teaching through interactions, and I hope I could convince you that this is a very promising approach for speeding up robot learning, especially if you're focusing on experts and narrow tasks. It really plays to the complementary strengths and weaknesses of human teachers and robots, but I also believe that can be very nicely combined with many other ideas you have in robot learning, using a large language model to come up with the correct sequence of doing things, pre-training stuff in simulation, using these kind of methods to collect better and more data for training generalist models that Francesco was talking about, and many, many other ideas. We wrote a massive survey paper on interactive imitation learning a year ago, roughly. So if you're interested in this topic, feel free to check it out. And one big open question is still really, how do humans like to teach a robot? We've done quite a few user studies, but that was really more about figuring out if our approaches work. But there we really saw a big difference is in how human teachers approach it. People that play video games tend to be very good at teaching robots in that way, but also in terms of preferences on how much information you give, how many options you give them, how many different ways of controlling and interacting with the robot. That differs very much and is a very interesting challenge. With that, thanks a lot for listening. You can see my team and other people that contributed to work I got to present today on the left, and on the right you have a few logos of the sponsors. Thanks a lot.